For nearly a century, quantum entanglement has been defined as an instantaneous phenomenon. Two particles interact, and at that moment, no matter how far apart they later become, they remain connected. This definition was mathematically valid, but it left a critical question unanswered. If entanglement forms between particles, how long does this formation actually last? Now, for the first time, scientists have found the answer to this question. Collaboration between physicists at the Vienna University of Technology and research teams in China has measured the birth of quantum entanglement. This process does not happen instantaneously. It occurs within a measurable time interval of approximately 232 attoseconds. This is about 1/20th of a second. This discovery does not change the laws of quantum mechanics, but it fundamentally changes the way we understand one of nature's strangest phenomena, presenting entanglement not as a mysterious instantaneous connection, but as a dynamic physical process with structure, timing, and observable stages. Let's now explore together how scientists captured one of the fastest events in nature and why this changes everything. The research did not start with the question of whether entanglement exists. That question has been answered for decades, but with a question about the process. Professor Joachim Bergdorfer and his team at the Institute of Theoretical Physics at TU Wien wanted to understand how entanglement begins. We want to learn how this entanglement develops in the first place and what physical effects play a role on extremely short timescales, explains co-author Professor Eva Brezinova. To investigate this, they turned to one of the simplest quantum systems imaginable, a helium atom struck by an ultra-intense high-frequency laser pulse. Here's what happens in this collision. When the laser hits the atom, one of its two electrons absorbs enough energy to escape completely, breaking away from the nucleus and flying off into space. But the laser's effect doesn't stop there. If the pulse is intense enough, it also disrupts the second electron at the same time, raising it to a higher energy state without ejecting it. This electron remains bound to the atom, but now occupies a different orbit and carries more energy than before. During this intense interaction, these two electrons, one escaping, one remaining, enter into quantum entanglement. What makes this scenario unique is the behavior of the escaping electron. In classical physics, you might think the electron leaves the atom at a single well-defined moment. However, quantum mechanics does not work this way. Electrons do not behave like sharply defined particles. They behave like waves. The escaping electron does not leave at a single instant. Instead, the wave function slowly leaks out of the atom, spreading into space over time. Brezinova says, the electron does not suddenly jump out of the atom. It spreads out from the atom like a wave, and this takes a certain amount of time. This spreading creates quantum superposition. The electron exists in multiple states at the same time. It has left the atom both earlier and later. From a quantum perspective, the electron itself does not know when it left. This departure time remains fundamentally uncertain until measured. But here's the interesting part. The energy state of the remaining electron is related to the departure time of the escaping electron. If the remaining electron stays in a higher energy state, the escaping electron likely departed earlier in the interaction. If the remaining electron settles into a lower energy state, the escaping electron likely departed later. The two electrons are linked not only in terms of their properties, but also in terms of time itself. Using highly sensitive quantum simulations, the research team calculated the time differences associated with these related states. The result, approximately 232 attoseconds. To put this into perspective, an attosecond is 1/100000th of a second. Light, the fastest thing in the universe, travels only the width of a hydrogen atom in 1 attosecond. In 232 attoseconds, light travels the diameter of a small molecule. This is the time interval in which quantum entanglement forms between two electrons. The team also designed an experimental protocol to directly measure this effect. This method involves combining two laser pulses. The first pulse creates the entangled electron pair. The second pulse arrives with precisely controlled timing, simultaneously examining the quantum states of both electrons. By measuring the energy of the bound electron and the momentum of the escaping electron together, researchers can reconstruct their shared quantum history and determine when entanglement occurred. Bergdorfer says, these differences are not only calculable, but also measurable in experiments. Several laboratories are preparing to test these predictions using current attosecond laser technology. This result changes the most fundamental way we think about entanglement. For decades, quantum theory has treated entanglement as something that simply exists when two particles interact. Textbooks define it as an instantaneous correlation. The particles become linked, and that's all there is to it. But this picture has skipped over the critical question of the process. How do correlations actually form? What are the physical mechanisms driving them? This research provides the missing temporal structure. Entanglement develops while quantum wave functions are still overlapping and interacting. Electrons do not suddenly become linked in a separate step. As the escaping electron moves away from the atom, the wave functions gradually overlap, and this overlap takes a measurable amount of time. This also clarifies a persistent misconception about quantum mechanics. When entangled particles are later measured at distant locations, their correlations emerge immediately, no matter how far apart they are. This situation has sometimes been misinterpreted as communication faster than the speed of light, or in Einstein's famous phrase, spooky action at a distance. However, nothing travels between the particles after they are separated. The connection was established earlier during the local interaction that created the entangled pair. In this experiment, this interaction occurred while both electrons were still inside the atom. The 232 attosecond timing precisely determines when the quantum states became entangled. After that, even if they are separated by light years, no new communication occurs between them. This is entirely consistent with the no communication principle of quantum mechanics, which prohibits signal transmission faster than the speed of light. What this work adds is the missing temporal picture, the moment entanglement arises. This discovery also relates entanglement to the broader field of attosecond physics. Over the past 20 years, ultra-fast laser technology has revolutionized our ability to study electron behavior in real time. Scientists have observed electrons passing through barriers, transitioning between energy levels, and responding to intense fields on the attosecond timescale. This work extends that capability to quantum correlations themselves. Entanglement is no longer just an abstract mathematical property. It emerges as a physical process embedded in the same ultra-fast dynamics that govern electron motion. Being able to time the formation of entanglement is a development with profound implications for quantum technology. Much of today's quantum engineering focuses on how to preserve entanglement once it is created, protecting quantum bits from environmental noise, maintaining consistency long enough to complete computations. However, this research opens a different door, controlling how entanglement is created. In quantum computing, quantum bits must be entangled in precise configurations for logic gates to function correctly. Understanding the formation dynamics could lead to cleaner entanglement, fewer errors from uncontrolled interactions, and more reliable quantum operations. In quantum communication, entangled photons are used to distribute encryption keys and synchronize distant systems. Knowing exactly how and when entanglement forms could improve the timing and stability of these quantum networks. The work also suggests that the structure of entanglement may depend not only on whether particles interact but also on how they interact. The shape, timing, and intensity of laser pulses can influence the resulting quantum correlations. This opens experimental avenues for engineering specific types of entanglement by adjusting interaction parameters. Beyond atomic systems, similar attosecond techniques can be applied to molecules, solids, and other quantum materials. Entanglement plays a role in chemical reactions, superconductivity, and even biological processes at the molecular scale. Understanding how it arises could reveal new physical properties in complex systems. This discovery also highlights how much structure is hidden at extremely short timescales. Processes once considered instantaneous reveal rich internal dynamics when examined with sufficient resolution. The next experimental tests will provide critical validation. The proposed measurement protocol relies on existing tools, nanosecond lasers, random detection of electrons, and quantum state tomography. Numerous research groups worldwide are currently preparing to implement these experiments. Success will not only validate theoretical predictions, but also establish a new standard for investigating ultra-fast quantum processes. Quantum entanglement is no longer just something that exists. It is something that is formed, evolves, and can be timed. With a nanosecond precision, one of the greatest mysteries of quantum physics has become measurable, opening new doors to understanding and controlling the quantum world.